the last class we had a brief introduction to photoelasticity, and I introduced photoelasticity by taking an example of a beam under 4-point bending. The focus was to show that the photoelastic fringes indeed represent contours of sigma 1 minus sigma 2. So, what is the advantage? If you have the stress field equations, you would be in a position to calculate analytically sigma 1 minus sigma 2 and plot it and see whether it compares with whatever that is obtained in the experiments. And in order to emphasize that crack is more dangerous than a circular hole or an elliptical hole, we also saw the fringe patterns. We will see those fringe patterns again. So, you have a plate with a circular hole, you have a plate with an elliptical hole, and you have a plate with a crack. And if I maintain the load as 7 in plate with a circular hole as well as 7 in the elliptical hole, the mere comparison shows the number of fringes you come across in a crack is much higher than what you see in an elliptical hole or a circular hole. So, the one way what we could take advantage of this is we are going to develop stress field equations in the vicinity of a crack, and we need to verify whether those equations are correct. So, what we could do is from the analytical equation get sigma 1 minus sigma 2 and plot them and compare with the experimental result and ensure whether our solution is correct. That is the reason why I said I would be using extensively photoelastic method for developing the concepts in fracture mechanics. If you really look at the history, the stress field equations have been improved by looking at the geometric features of the photoelastic fringe. And I have also asked you to look at the special features of the fringe in the vicinity of the crack. Let us look at the features of the fringe. This is the crack and we will take this as a reference axis. About this axis, the fringes in the top and at the bottom are symmetrical. The other striking feature is the fringes in the top are tilted forward. Keep this geometric feature in your mind. As soon as we develop the stress field equations, we would plot contours of sigma 1 minus sigma 2 and compare with the fringe patterns and see what we obtain. Let us wait till such a moment. Now, let us go and look back the historical development, and if you look at study of elliptical holes in a tension strip by Inglis was done in 1930. And what was the important emphasis from his work? If you look at the history, the first problem leading to stress concentration was solved by Kirsch. It was in 1898. He solved the problem of an infinite plate with a small circular hole. This was possible because you had the development of polar coordinates as well as Cartesian rectangular coordinates. So, the hole can be modeled from a polar coordinate. You can easily identify the boundary condition on the hole, you can easily specify the boundary condition on the hole. So, the first problem was solved by Kirsch for the case of a circular hole in a tension strip, and it took almost 15 years for Inglis to go and repeat the same for an elliptical hole. So, the moment you go to an elliptical hole, you need to specify the boundary conditions on the boundary of the hole, and they had to develop elliptical coordinate system to conveniently handle the problem, and that alerted the importance of a crack. Let us look at very closely, and I would like you to make a neat sketch of this. I am showing it in a finite screen. So, imagine that this is an infinite plate with a small elliptical hole, but it is shown big for clarity, and also there is also a small pixelation error here, the figure is magnified. So, you find that there is a shift in this, you imagine that this as a straight line. So, what you have here is, in a tension strip you have an elliptical hole, and this shows the typical variation of the stresses on this axis, and you have the variation of sigma xx, and Inglis found that this is related to the far field stress by a factor 1 plus 2a by b. This you might have heard in a course in strength of materials. The moment when b tends to 0, the multiplication factor goes to infinity. What is the meaning of that? One meaning is the stresses go very high, other meaning is the methodology of stress concentration to ascribe to a crack no longer is valid. You need improved mathematical approaches to handle the problem of a crack. And what is the advantage of an elliptical hole? You can verify whether the solution is correct by changing the minor axis. If I make the minor axis equal to the major axis, I would get the problem of a plate with a circular hole, and if you make b equal to a and this goes to 3. And this is what was obtained by Kirsch way back in 1898, and you find when you have a circular hole, the maximum stress is 3 times the far field stress. So, you all know stress concentration factor is 3, and for an elliptical hole you can calculate the stress concentration factor. The moment when you make b tends to 0, you have the modeling of a crack, and what is summarized here is one requires newer approaches to handle such a problem. Now, let us come back. Suppose I have a plate with a hole, you will have only stress concentration until the stresses reaches a maximum value, failure will not happen. On the other hand, when I have a crack, what does it show? The values go to infinity. In reality, nothing can go to infinity. At the most, the stresses can reach the plastic condition. This is what you can anticipate. The direct interpretation of English will only alarm you that nothing can remain in solid form if I have a crack, because even for a very small load you will have an infinite stress. It may eventually break into pieces, but that is not the way you come across. In reality, you have structures, they have embedded crack, but they do not make the structure as a powder. That is what English result shows if you look at it on the face of it. In order to explain why structures remain with cracks, Griffith was able to come out with a theory that you need energy for the crack to grow. That was a contribution by Griffith in 1920. He was particularly interested in propagation of cracks in glass, and he could develop right ideas for crack growth. This is very important. He was able to penetrate and say English solution is very important, it alerted that crack is more dangerous, but it provided a logical explanation that you will have structures with crack. Just because it has a crack, you need not have to discard. The cracks will grow in surface, attain a critical dimension, only then fracture will occur. And we would see a large number of practical cases when you do postmortem, you would see distinctly a crack growth region followed by fracture. So, the contribution of Griffith in 1920 was very important, and as I mentioned, he formulated that an existing crack will grow provided the total energy of the system is lowered by its growth. So, you have to appreciate the existing crack will grow, and eventually when it becomes critical, fracture will occur. So, it is not that when you have a crack, when you apply even smallest load, the structure is going to fail, it is not so. The contribution of Inglis, you have to appreciate, he was able to bring out analytically that crack is much more dangerous. Even though Griffith was able to formulate his ideas, his work was not noticed at that time due to the exigencies of the world war. It happens, somebody does scientific work, only if there is peace all around, people will notice what is his contribution. And after the world war, there was also depression. So, people were worried with day to day living. So, they were not really worried about science. So, it was not noticed. And there is also another aspect to it. See, Griffith was not able to coin a convenient parameter. See, for the development of any field of science or art, you need to develop jargons. Jargons are very important, and the moment you listen to the jargon, you immediately understand what it conveys. So, you need to make a convenient parameter. Until then, fracture was not looked at by people. That contribution was done by Irwin, and that came about way back in 1948. So, 1920 or 22 Griffith did all these experiments. Only in 1948 Irwin extended this to ductile materials. Whatever the work that was done by Griffith was on glass. So, what you will have to appreciate is the contribution of Inglis is also very important. The understanding of Griffith is good, he had right ideas for crack growth, but he was not able to express it in a convenient fashion. And let us look at some of the very interesting examples. Just watch this animation and identify what this animation is trying to show. Now, you have seen it, let me ask the question, do you see that there is a crack in this plate? And what happens then? This is actually a ball pen, you press it, you find what happens to the crack. The crack grows in length. The moment I remove the load, you find there is a semblance of healing of the crack. In fact, in brittle solids like mica and glass, Griffith observed when the loads are removed, the crack heals. See, this is very advantageous for us. Suppose I want to go and do an energy method, it is easy for me to formulate the equations if I have a reversible process. See, if you look at fracture, it is intrinsically non reversible, because in an actual solid you will have plastic deformation, energy is dissipated and you can't come back to the original situation at all. In highly brittle solids, people have found under suitable conditions the crack can heal. If you recall, in the energy release rate, I said I want to find out what is energy required for the crack to grow. I said I am going to close it, find out energy required to close, I will use it for finding out what is energy required for crack to grow. So, in order to go to that kind of a mathematical manipulation, this helps. In fact, this was an accident in our laboratory, and I quickly got that recorded and included it as part of the course material. And let me take one more example. Here I am showing a glass plate. I have just thrown a stone in this place, it got broke, and then I use cellophane tape to put them together and bring it to the class. What do you see here? By putting a stone, I have pumped in energy to this glass, and glass has to dissipate the energy. What way it is done? You have some material removed in the core and you have several branches of crack. This is very important. If I develop a fracture theory, the fracture theory should be able to say how many cracks in which direction should develop and grow. We should have that kind of an answer. A commoner will only say the glass is broken, replace the glass. A scientist has to go and see how the energy has been dissipated, how many crack branches have come about, and how to deal with this. And I will show one more example. This again you just watch the animation. This is again in a sheet of glass. I will repeat the animation again. It conveys a very important message. What you have is, I had one crack which was having a particular speed, then suddenly it branches out as two cracks. I will repeat the animation, you just observe it. The crack speed increases, suddenly it becomes 2. So, from fracture mechanics point of view, what you will have to look at? If I develop a fracture theory, the fracture theory should be able to say why a crack branches out. In fact, if you have closely looked at the animation, the crack speed was increasing. So, when the kinetic energy was more than what it is, the speed was increasing, and it has been established by photoelastic analysis using dynamic photoelasticity that the crack can take only the Rayleigh wave speed, it cannot go faster than that. So, more energy cannot be dissipated. So, if more energy has to be dissipated, the crack has to branch out. So, that is why I said photoelasticity is very closely linked to development of fracture mechanics. So, there is an upper limit with which a crack can grow in a material, that is decided by the Rayleigh wave speed, and this was first brought into focus by Kalthoff. He had done a series of experiments using the method of caustics. These are the caustic shadow that you get in a experiment by caustics, and you can again look at the animation. The animation shows that crack speed increases and it branches out. In this we have already noticed that fracture mechanics is a broad area covering several disciplines, and you have material science, non-destructive testing, stress analysis and design, and we would see one after another what you will learn in each of these aspects. The material science covers fracture, whether it is a cleavage fracture or a ductile fracture, the fracture process, and also measurement of fracture toughness. These three aspects come under the topic of material science. In non-destructive testing, you will have to find out how to detect a crack and also how to monitor the crack, what should be your periodic interval to go and monitor the crack. And finally, we come to stress analysis and design. In this you have several issues. We would develop the stress field, using that as an information and also the information on fracture toughness, we could go for improved design methodologies, and we had already seen fracture mechanics has to help us to have damage tolerant design approach. So, in this you have two main categories. One is a safe life design. See, in conventional analysis, when people were thinking about fatigue, they wanted to have infinite life. infinite life is not possible. What we are saying here is within the life that is anticipated, the structure is safe. This is the way we are looking at. So, this is a different approach. Another way of looking at is when you are having difficult installations like nuclear power, where any accident can lead to catastrophe, you would like to invoke what is known as fail safe design. One is a multiple load path. You do not want to have a structure to fail if one member fails. A good example is, suppose you make a castle out of the playing cards. People have such competitions. You just go and blow or remove one card, the whole structure will collapse, and you do not want to have your structural systems to collapse like that. You need to have multiple load path. And I used to mention, if you look at your own human body, God has given you with 2 kidneys. If one kidney fails, you can still survive, another kidney can help you. Okay. So, you find even in natural systems there is some kind of a essential redundancies inbuilt. So, by looking at optimization, do not stretch optimization beyond a limit. So, you need to have multiple load path. Suppose I have a crack, I must also have the design to arrest the crack. We must have methodologies to arrest the crack. And finally, there must be some kind of a warning before the structure is about to fail. So, you have what is known as leak before break, abbreviated as LBB, and LBB criterion is very, very important in nuclear technology. Unless the components go through LBB criterion, they do not permit those components to be utilized in nuclear power installation. So, you can feel safe. So, science is used. So, this is what we have been emphasizing all along. Fracture mechanics attempts to account for the existence of inherent flaws in structures, and thus is closer to reality in modeling engineering problems. And how does this do? It uses stress analysis to determine the stress intensity factors. We have still not looked at what are stress intensity factors. We would develop the concept, and it uses material science to determine the fracture toughness, and non-destructive testing to determine the initial flaw size. So, this is very important. So, what we will go about is, when you say a non-destructive testing, we will see what is the minimum size it can detect. So, that would be the assumption on what is the initial crack size, and we would do theoretical calculation. So, if you have a better non-destructive testing, even our fracture calculation would be much better. So, NDT development is also equally important. With all that information, it is possible to design a structure to give a safe life. And once you come to fracture mechanics, there are 2 broad categories that you can think of. One is linear elastic fracture mechanics, another one is elastoplastic fracture mechanics. The whole of fracture mechanics focuses on structures made of ductile high strength alloys. This is very important. You do not apply fracture mechanics to mild steel, only for high strength alloys fracture mechanics is applied. The high strength alloys fail in a brittle fashion has prompted the birth of fracture mechanics. This is what I had mentioned earlier. Whatever the ideas generated by Griffith for brittle solids was extended to ductile high strength materials by Irwin in 1948. We would see how he has done it. When we look at the chapter on energy release rate, we would be able to find out how conveniently he was able to extend the ideas of Griffith. And what did Griffith do? See, when you look at English solution, he alerted crack is very important. So, people are thinking crack is important and they were trying to generate ideas, but they were missing a very important point, which was pointed out by Irwin. He shifted the focus from the crack to the crack tip. Then the whole of fracture mechanics became very simple. So, what he did? By moving the analysis to the crack tip, he devised workable parameters like stress intensity factor and energy release rate. So, that was a very important contribution by Irwin, and even in one of our earlier class, we have shown that when you have a crack, I showed that crack tip is taken as the origin, crack axis as taken as the x axis. So, all that comes from contribution by Irwin. Just because he shifted the focus to the crack tip, we were able to get convenient parameters relatively, because if you look at stress intensity factors, it has very funny units. Leaving that apart, compared to what Griffith was trying to say, what Irwin said was easier for people to understand. And we have already emphasized that the moment you have a crack, you will have very high level of stresses. So, definitely there will be plastic zone developed, and if you look at LEFM, this accounts only for small scale yielding near the crack tip, and this abbreviation SSY is also a very important abbreviation in fracture mechanics. So, when you come across SSY, you should understand that it refers to small scale yielding. You have plastic zone very highly localized. This is what you have to appreciate, because if you directly extend English result, you would get confused. The structure would have become a powder, why it still remains as solid. That explanation was provided only by Griffith. Even though you have very high stresses, from a practical point of view, it cannot become infinity. If it is a elastoplastic material, it will either become plastic or it will have some work hardening, some such aspect will happen. You will not have infinite stresses there, but the plastic zone is very highly localized. If it is very highly localized, then LEFM is applicable. If it is spread slightly, then you will have to go in for EPFM. We will classify LEFM as well as EPFM based on plastic zone also. The use of LEFM is found in aerospace structures, because you use essentially thin structures, and by and large it is more of a thumb rule. Some aerospace components you will also require EPFM, but by and large LEFM is applicable to aerospace structures. As I mentioned, if the plastic deformation at the crack tip is high, then EPFM is what you have to look for. For situations where material behavior is non-linear, such as in nuclear applications, EPFM is essential. You could also classify LEFM and EPFM based on which material you are dealing with, and I would like you to take down the notes of these slides. And when you look at LEFM, if I use high strength steel, precipitation hardened aluminum, polymers below glass transition temperature, ceramics and ceramic composites, for all of these materials you could comfortably go and attempt LEFM. If it fails, then go for EPFM. These are all thumb rules, these are all not rigid rules. It depends on various factors, it depends on thickness of the specimen also, but this is more like when I have a high strength alloy, how do I go about and pick out. And polymers are also becoming very important these days. When polymers are becoming very important, you will have to know until what condition you can analyze it based on LEFM, and we find polymers below glass transition temperature, you could invoke LEFM. If it is above glass transition temperature, then you will have to go for EPFM. So, you have some kind of a guideline, you will have to take this more as a guideline rather than as rigid separation of the typical materials for which EPFM or nonlinear fracture mechanics is applicable are low and medium strength steel, metals at high temperatures or high strain rates, these are all becoming very important. High strain rate is becoming very important when people want to find out safety of structures due to bomb blasts. So, these are all happening at very high strain rates. So, you need to have proper modeling, particularly nuclear installations should be safe from a bomb attack. Polymers above glass transition temperature, ceramics at high temperatures, because in gas turbines people want to improve the thermal efficiency. So, they want to push the operating temperature as high as possible, and ceramics are being used. Ceramic is basically a brittle material, but if it is used in high temperature application, LEFM is not sufficient, you will have to invoke EPFM. This is again a guideline. So, you have to be very careful. Now, what we will look at is we will classify LEFM and EPFM based on the plastic zone, and certain ideas you will also get. The plastic zone is very small and highly localized, and this shows a small schematic of what would be the nature of the plastic zone, and I have this for high strength material in plane strain, then I have high strength material in plane stress. If you watch it carefully, the plastic zone in the case of a plane strain is much smaller than what you have in the case of a plane stress. See, in conventional design, you say if the material yields, you consider that as a failure. I have already said, before you define what is failure, you will have to understand your application. Depending on the application, you establish what is the meaning of a failure, then go and look at the design. In the case of fracture mechanics, when I have a crack, you will invariably have plastic zone at the crack tip. The plastic zone is highly localized, and in fact, if the plastic zone is slightly spread as in a plane stress condition, it is beneficial from fracture mechanics point of view. The structure as a whole will still remain as brittle only. I mean, when you apply the load, it will have elastic response, it will not have a plastic response, but near the crack you will have a plastic zone, and that plastic zone dictates how the crack is going to behave. And in fact, in fracture mechanics, if you have some plasticity near the crack tip, it is beneficial, it prevents the crack to grow easier. Okay. So, it is good from the point of view of safety. Then we have another set of material which is more ductile in plane stress or plane strain. You have still higher plastic zone, and you also have situations where the plastic zone is visibly spread. I would like you to make a neat sketch of this. This brings out in nutshell the role of plasticity in fracture analysis. So, if I have a ductile material with spread of plasticity, until a certain point you can apply EPFM, beyond a point you need to go for plastic collapse, because certain structures can fail by plastic collapse. So, you have to find out whether the failure is precipitated by fracture, that is material separation, or even before fracture occurs, plastic zone spreads on the entire structure, and that is the reason why you have failure assessment diagrams are used in fracture analysis. They want to find out whether it comes in the category of plastic collapse or fracture. So, this kind of approach is needed when you have to handle practical problems. So, this gives an overall idea how plastic zone indirectly dictates which type of theory you have to invoke as a first approximation to handle the problem. Then we move on to the important aspect, that what are the modes of loading near the crack tip. This is again a contribution by Irwin, and he observed that there are 3 independent ways in which the 2 crack faces can move with respect to each other. You do not have to write these animations currently, we would see each one of these modes, you write only these points. The corresponding modes are labeled as mode 1, mode 2 and mode 3. There could be 3 independent ways in which the 2 crack faces can move, and these are labeled as mode 1, mode 2 and mode 3. And what is the beauty of this concept is the 3 modes describe all the possible modes of crack behavior in the most general elastic state. So, you will have a combination of mode 1, mode 2, mode 3 of various proportions in a generic problem. It may be only predominantly mode 1 or predominantly mode 2 or predominantly mode 3 or a combination of this. And what we would see now is, we would go and investigate and understand what happens in each of these modes and how they are labeled, and which one of them is more dangerous than the other, what way the other modes play in crack propagation. You make a neat sketch of this crack that is opening, this is very important, and what is shown here is the crack faces open up like this. The displacement of crack faces are perpendicular to the plane of the crack, and this is labeled as mode 1. This is also called as opening mode, mainly because you have the crack and the crack opens up like this, because of the load the crack opens up like this. This is one of the most common and dangerous modes of loading for crack growth. People have developed theories and showed that crack will eventually take a path such that the loading is perpendicular to that. So, mode 1 loading is the most dangerous, and even when we want to find out the stress field equations, we would develop the stress field equations for mode 1, then followed by mode 2 and mode 3. I hope you have been able to make the sketch with reasonable accuracy. Then we move on to mode 2, which is also known as a sliding mode. And you could see here in this animation, this is the crack and the crack surface slides. There is a sliding in the plane, and you call this as in plane shear mode or sliding mode. The displacement of crack surfaces are in the plane of the crack and perpendicular to the leading edge of the crack, and that is very clearly seen in the animation. And if you have the crack, the crack faces are sliding, I mean they are sliding like this. You have the opening mode, you have the sliding mode, the third mode is it is tearing like this, it is out of plane shear, that is what we are going to see. I hope you are able to make a sketch of this, you can make a reasonable sketch. And what is shown here is displacement of the crack surfaces of a local element containing the crack front. We have not shown the entire object, the external loading may be anything, we are only looking at what happens in the vicinity of the crack, how the faces move. Depending on that you label them as mode 1, mode 2 or mode 3. In fact, if you go for bimaterial problems, apparently external opening mode can also cause a sliding of the crack faces. So, it depends on the problem, we are not looking at what is the external loading, we look at only in the near vicinity of the crack. This is the tearing mode, also called as mode 3, and you will find the crack faces are like this, they move in this fashion. It is called as out of plane shear mode, this is also called as tearing mode, and we have already seen paper is usually separated by a tearing action, because if somebody gives you a sheet of paper and asks you to separate, you will not pull it like this, you will make a fold and tear it like this, and that is much more convenient, and paper fails easily by tearing action. And one of the challenges in early understanding of fracture mechanics is, in a given problem of external loading, if you have a crack in that structure, what kind of loading exists near the crack faces, whether it is subjected to mode 1 loading, mode 2 loading and mode 3 loading. In fact, one of your assignments gives a series of common design scenarios where you have a structure with known type of loading with cracks located in various fashion. You have to find out, because of the external loading, whether the crack experiences a mode 1 loading, mode 2 loading or mode 3 loading from fracture mechanics point of view. It is not trivial, you will have to have some kind of a training. And what is the summary? I said that you need to have what is known as a stress intensity factor, although we may not define it now, you will know what it is. For each of these modes, similar to the stress concentration factor, you could identify what is known as a stress intensity factor, which dictates the strength of the stress field in the near vicinity, and this is labeled as K1, do not read it as Ki. This is one of the common mistakes people do. You have to read this as K1, read this as K2 and read this as K3. So, for a given loading, you find out what is the value of K1, what is the value of K2 and what is the value of K3. From a material test, you find out what is the fracture toughness for mode 1, mode 2 and mode 3, and they are labeled as K1C, K2C and K3C. The C denotes it is a critical value, and this is considered as a material parameter. And I had already noted, see, in the case of simple strength of materials, what did you do? When you had combined loading, you invented the concept of principal stresses and you utilize the result from a simple tension test of the yield strength, and you find out how the failure will occur in combined loading. You do only one test. So, similarly in fracture mechanics, when we go and look at fracture theories, even though we talk about K1C, K2C, K3C, people find out K1C and try to find out how well it can be utilized even to predict a combined mode failure. That is why I said there are commonalities between your conventional strength of materials as well as in fracture mechanics, because we would like to practice what we understand and so it should be simple enough to practice. That is why we go in for it. We are not looking from a mathematical point of view that I need all these parameters, only then I will go and design. It is not the way design works. You have to find out a simpler procedure for you to implement it, so that you are well within the limits. And now we can ask, when I do a course in fracture mechanics, what are the answers that I could get from fracture mechanics is the question that you can ask. So, the first question is, what is the critical length of a crack? You can't say I will wait for the structures to fail and find out what is the critical length of the crack. You have to predict. That means you have to develop the fracture theory, you have to understand what way the crack will behave, you have to get the material parameter, and you should be able to predict for a given type of loading and situation for that structure this crack is critical. And another important point which you have not noticed, see, when I had shown the modes of loading, I have taken only one crack. In the idealization, what we said, in strength of materials you have idealized that it is an elastic continuum, you found that there are no discontinuities or inclusions in the material. The moment you come to fracture mechanics, you recognize the role of inherent flaws. When I say inherent flaws, I can't consider only one. You will have many cracks in the structure. Later on, as you develop the theory, you will realize what we are really looking at is, among this, whichever is the one which is critical is the one which we look at in our modeling. That is the way you can analyze. That is the way you can analyze it to start with. Now you have studies, if I have multiple cracks, how do they interact, which way you have to go about, what should be the design methodology, all those issues are being addressed through research. So, the first question is, what is the critical length of a crack? The second question is, for a given crack length, what is the residual strength? Then what is the time that would take for a crack to grow? And this is very important for you to answer the next question. The next question is, how is the NDT schedule decided? And I had already shown that crack can branch. What causes the crack to branch? And finally, what are the energy dissipating mechanisms? So, this puts a focus what you should be able to answer at the end of this course. If you are able to answer these questions, then you have reasonably understood what is fracture mechanics. So, in this class we started with severity of the crack indicated by photoelasticity. I also mentioned photoelastic contours are nothing but contours of sigma 1 minus sigma 2. So, when we develop the crack stress field equations, it is possible for us to plot sigma 1 minus sigma 2 from the analytical solution and compare it with the experiment and see whether our solution obtained is good enough, or do we have to take higher order terms, and such questions have been answered by conducting experiments on photoelasticity. Then we looked at historical development of what was the contribution of Inglis, what was the contribution of Griffith, and how Irwin extended it. Then we had a brief outline of how to classify LEFM and EPFM, and finally we had seen some fractures in the case of glass, and we raised certain questions that needs to be answered as part of this course. Thank you.